Righto guys, so far in the channel we've done a lot of fiberglassing work, a lot of boat building and everything else, doing hull extensions to my big 29-foot Australian built black fan, and then we've got a little Vickers Easy Rider that I've turned into a centre console, and we've got a shark cat that's on the go. But fiberglassing is only just the very beginning of doing, you know, a lot of DIY projects, so I thought I'd get more involved in the electrical side of it. I have been doing some electrical videos up till now, but I want to dig down deeply into the electrical side. So what I want to do is go back to basics, I guess, go back to basics and just talk about the very basic concepts and the ideas and what everything is. We'll look at the terms, naming conventions of all of the different systems that we're going to be using on my boats anyway. So as a part of that, I've got a battery sitting here. I've got an NMEA 2000 starter kit, so we're going to talk about protocols. What is a protocol, you might ask? Well, hang around and you'll find out. We've got a couple of Suzuki gauges. So let's get into it. Essentially, I'm going to start right at the very nitty gritty basics of it, and we'll talk about voltage. We'll talk about the current, we'll talk about resistance, we'll have a look at power, and a lot of other things. When we talk about voltage, what I like to do is I like to describe it as the potential difference. So when we talk about a potential difference, we're looking at the difference between one point and another point. And it doesn't have to be, here we've got a battery and we've got a zero or a negative terminal and our positive terminal. Now when we put a multimeter across that, so we're going to switch our multimeter to DC, so there's 2 clicks over, bang bang, voltage DC, and we basically grab it and go boom boom across each of those. Hopefully you can see what is that, should be 13.59 volts. Now the good thing about these DVMs, digital voltmeters, is you don't have to worry about the polarity. So I can come along and put my positive lead on the negative terminal and vice versa. What I want to explain is what we're looking at is essentially the potential difference between those 2 points. So electrically, this is at 0 volts and this guy here 13.59. So the potential difference, 0, 13.59, so the potential difference there is obviously 13.59 volts. Okay, so there's a lot of little images out there on YouTube, and I'll whack a couple up and we'll go through those and explain those. And they can be very, very helpful too to understand the difference. So the voltage is the potential difference between 2 points. The voltage does not have to be, just keep in mind, when we're measuring the potential difference of the voltage, it doesn't have to be on a negative or a positive. It can be anywhere within that circuit. So sometimes when I'm looking for a fault and a circuit, it doesn't matter what sort of circuit it is, what I'll do for a fuse, for example, is I'll whack my multimeter straight across that fuse. Now I've got a fuse here that I can show you at the moment, but it gives me straight up, gives me an idea of whether or not that fuse is okay. Now you can pull that fuse out, have a look at it and go, oh, that's blown, throw it away, put another one in. But sometimes it's just quick bang, 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 bang to go through and test each of your fuses. Now if you've got power onto your circuit, you've got 13 volts on one side of a fuse, what should you have on the other side of the fuse? 13 volts. So if you've got a ground reference point, you can measure that. You go boop, 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 boop. Yep, easy, nice and easy. But if you haven't got a ground reference point, just go straight across the fuse. Because if that fuse is okay, you're going to have a 0 volt drop across that fuse. So the potential difference will be 0. If the fuse is blown, however, the potential difference from one side of the fuse to the other side of the fuse is going to be whatever your supply is. Or whatever it might be 12 volts, 24 volts, 36 volts, 48 volts, whatever it is. So that gives you a little bit of an idea maybe, and the same applies with switches and other hardware. So, and then we talk about the current. So again, we'll have a look at the little diagrams that I was talking about. Hopefully I'm not going to get into trouble for. When we talk about current, we're talking about the number of electrons that go past one particular point. And when I say that, we use, back in the 1980s, when I did my apprenticeship, we used what we call conventional current flow. Now that's sort of old terms these days because everybody uses, well, a lot of people use electron flow now, but conventional current flow is how everybody thought it worked back in those days. So conventional current flow is the electrons flow from positive to negative. With 40 years of being in the industry, I have never ever had to worry about the fact that, hey, actually that's wrong. Electrons actually flow from negative to positive because the electrons want to be positively charged, right? So who cares? To be completely honest with you, the way that I look at it is sometimes there are things that, yeah, okay, you're taught when you do your apprenticeship or when you do your training, but then you just forget about it. You walk out the door and go, yeah, all right, I'll never use that again. And that's probably one of them. It's important to know that, yes, we have electrons flowing through a circuit, and without the current, without the voltage, we're not going to have any current flow. Okay, and then the other thing that we've got is resistance. So when we break it down, the way that I like to look at it, resistance is basically any sort of barrier that's going to slow down or prevent current from flowing through a circuit. All right, and again, there's a lot of different analogies out there to show you what resistance is. And the classic is, or the easiest one, is probably a garden hose. So here's another way of looking at it. I've got a garden hose here, simple garden hose. I've turned the tap on, I've basically crimped the hose, right? So I've got maximum resistance there. Now, let's say that the tap or the supply of the water, the source of the water, is our voltage. All right? Now, with no resistance, I've got full current flow. Our water is the current. In this case, we've got no resistance and we've got full water flow. What happens when I start to increase the resistance? Pretending for a minute that water is our current, and I start to increase the resistance, it starts to slow right down until, let's say it's open circuit, we get very little current flow at all. So we open it up again and decrease our resistance, decrease the resistance, current starts to flow again, and there we go. So resistance, increase, decrease. Increase the resistance, decrease the resistance. I hope that makes sense. So hopefully, guys, that makes sense. Now, there's a formula that we use, which is called Ohm's law, where we can work out the different variables. If we know two of those variables, so voltage, current, resistance, if we know our voltage and our current, we can work out what the resistance is in that circuit. If we know what our voltage is and our resistance, we can work out what our current is going to be. And then we're going to have a look at our power laws of power. So power in watts. So I should mention as well, so volts is volts. It's typically shown as a V. Current is shown as an I. I've never really cared about that. I've always written A, amps, current, amps, and R for your resistance. So power is the combination, power is measured in watts, and power is the combination of your voltage and your current, the total energy consumption within that circuit. So that's your power. All right, simply put, easy, simple put. I'm not going to get too deep into some of these because this is just a skim over the top to give us a bit of an idea of what we're talking about. Hopefully what we're going to be able to do is get you to a point, if you're happy with your fiberglass and everything else but you've got no idea about the electrical, hopefully by the end of this you're going to be able to go and do the whole lot. Do your boat rebuild, do your boat repairs, do your electrical work on your boat, and Bob's your uncle, you know what I mean? So all good. So power, we talked about power, and then we've got a lot of other terms that we use. Some of the terms, frequency. So in our modern electronic systems, frequency is something that's very important, especially when we're using fishing sonar systems. Our systems use different frequencies, and I'm not going to go into the exact frequency spectrum or the range. I'm just going to talk about high and low frequencies. So typically what we have is a low frequency has a very wide bandwidth. So frequency is essentially the number of times, let's say we've got a sine wave, and it's the number of times that sine wave changes direction. Okay? It does a full cycle and changes direction. Low frequency has a very wide bandwidth and can travel further. It can travel further through air, it can travel further through water, it has a wider bandwidth so you can see more or hear more. Let's liken it to something like, I don't know what sort of music you listen to, but doof, 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 your doof, doof music. The doof, doof, the low frequency bass of that sound travels further. You can hear it a lot more. If you're at a concert and let's say it's a windy day, what typically happens is the high frequency component of the music tends to sort of dissipate a lot quicker, and you just hear this doof, 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 doof in the background. That's because, again, that low frequency sound just travels further. And the same sort of thing applies underwater. We got our transducer that's sending our signals through the water to the bottom of the ocean floor. Let's say it's very deep. We're going to try and use a low frequency system to basically have a look at what we're trying to find, whether it's at the bottom, we want to have a look at structure, whether we want to find fish or whatever it is. Then we're going to use a transducer at low frequency and deeper waters to try and get that better image. But we've got chirp and high frequency, well, lots of different technologies these days. So your high frequency is a lot faster, so it's like this, right? And it's a lot narrower. The problem with that is it can get lost very, very quickly, dissipates through air. Like I was saying before, when you're at a concert or you're listening to music, you'll notice that the doof doof, or the low bass, low frequency sound is more prominent, and you can hear it a lot better, and the high frequency stuff tends to disappear a little bit and dissipate. Same applies in the water. So something to think about is, if we're in shallow water, flick it up, use our high frequency. It depends on what you're using it for too. We'll go through that a little bit later. But our high frequency in the shallower waters, and then our low frequency if we want to really penetrate those water columns and get right down deep. So protocols, that's frequency. Protocols. What's a protocol? So a protocol is something that we're going to need to know if we're going to wire up our boat, especially if we've got electronic systems on board. Now, so there are a few different protocols that we don't have to know the ins and outs of it all. All we really need to know is that, okay, my boat has got an NMEA 2000 system on it, and it's got a CAN bus, and it's going to have Ethernet, and it's going to have Wi-Fi, and it's going to have lots of other things, right? So all of those different things, our NMEA 2000, our CAN bus, our Ethernet, our Wi-Fi, all of those different, and our Ethernet, did I say Ethernet? I don't know. And our Ethernet are all just different versions of different protocols. Hope I said that right. Hope that makes sense. It does in my head anyway. And the reason that we have those protocols is because they've got a set of rules that apply to them. Basically, some of those protocols are slow, so the data transfer speeds are relatively slow, and they're not great. They're good for instrumentation and everything else. For NMEA 2000, classic example, if we want to have a look at our engine data, fuel levels, depth, water temperature, that sort of stuff, then NMEA 2000, spot on, no dramas, or even a multi-function display that sits on an NMEA 2000 backbone. It's great, very versatile, used a lot in the marine industry, but it has its limitations. And by its limitations, I mean its speed at which it can operate. So once we get above that, or we want to have a look at pictures or images or something that has high speed data transfer rates, then we've got to have a look at a different protocol. And that protocol is, we'll start talking about Ethernet. So the Ethernet is a completely different wiring system. It uses typically Ethernet, well not typically, I've never seen an Ethernet system that doesn't use 4 pair twisted cables. So total 8 wires within that cable, and you've got 4 pairs, so 2 wires twisted together. And the twist is there for a reason. The twist is there. We've looked at things like electromagnetic induction, and then there's a lot of other things that we're trying to avoid. We're trying to control. We don't want noise generated into those cables. So anyway, I don't want to get too deep into that, but I guess Ethernet is our high speed. It's typically what we use on our computer networks. It's a copper system. You can use fiber optic cables. You've got single mode, multi-mode fibers. You can have them on a boat as well. There's nothing wrong with that. Ethernet goes from there. And then we've got our CAN bus. So the CAN bus, fly-by-wire is a classic example. So my engines are Suzuki. and they use a fly-by-wire system, and that fly-by-wire system uses CAN bus. So again, we'll look at that maybe a little bit later and not get a lot deeper into it. So when we have a look at the Suzuki wiring diagram, for example, you can see that it uses CAN bus. So what it does is what we've got a boat control module, which is the main head end. Let's say it's the master computer, and then we've got our ECUs, engine control units or engine control modules, whatever you want to call them. I don't really care. It's a lot of people, these acronyms these days, man, so many of them, I just get so confused. Even you know, even today, I just get so many acronyms, and oh man, it does my head in. Well, I got a little bit carried away there about the acronyms, didn't I? But anyway, back to the CAN bus. So essentially the CAN bus is a protocol that allows our boat control module, the BCM, little computer, to talk to the engine control units. So the boat control module that might sit up in the cabin somewhere on a flybridge or whatever can talk to each of the engines. If you got one engine, talks to one engine, two engines, yeah, you get the story, right? So basically that's all it is, just another protocol for those systems. And the CAN bus can be used in a lot of different applications. So, but anyway guys, I hope, I'm going to end it up there now. I hope you got a little bit of information about that. I wanted to go back to basics so that the basics are there, and then what we're going to do is we're going to go back through some of those. We're going to talk about Ohm's law a bit more, why we need Ohm's law, how we can apply Ohm's law to what we're doing on a boat. We're going to have a look at the power calculations and everything, and hopefully we're going to be able to build on a lot of that and add a lot more content to that. So essentially my intent is that over a period of time, a lot of the information will get stuck together and it'll make a lot more sense. So we'll go back over some of those theoretical sections. We'll have a look at some practical things, our cabling, our cable management systems, our cable protection systems, and a lot of different other things. Alright guys, I hope you got something from that, and hope you'll see you in the next one.